Alright, I wanted to make a video here where I talked a little bit about fitting parameter values for models. So we use models a lot in environmental engineering applications, also in just most kinds of engineering designs. And so I came up with a relatively simple model. I had presented this model before as an example of different kinds of variables that you might encounter when you're doing modeling for environmental systems, and I made another video about that. You might want to watch that before this. In any case, that model, the basic model has an equation that looks like this here, where we have, if the u was on this other side, it would be u dc dx is equal to negative kc. And so this might represent pollutant transport from some sort of pollution source in a river downstream. And we're saying that it's plug flow, meaning that there's no mixing of the stream. So as the water flows from here to there, it doesn't kind of mix around. It just stays in its separate little packets, and then as it moves, it's decaying at a rate that depends on how much the concentration is. So this is a problem that's studied a lot in environmental applications, and to solve it, because it's a first order with respect to x, we need an initial condition on x, and that would be c at x equals 0 is c0. And so then you can go through and solve this with separation of variables, and you end up with this c of x equals c0 e to the minus kx over u. So this would be our model for the pollution concentration starting from the source. So if I put in x equals 0, it's c0 at the beginning, and then as it goes downstream, it's going to kind of die off, depending on how big the value of the decay coefficient is and the velocity. Anyway, so this model, as I talked about in that video, it has one independent variable. So when we're looking at these variables, again, as I talked about in the other video, you've got independent variables. Those represent the domain. That can be space and time, x, y, z, r, phi if you're in cylindrical coordinates, and circular and spherical coordinates, etc. So here we just have x, one independent variable, and then we have one dependent variable. That's the thing that we're predicting as we go from one point to another here. And so here's like some observations here in a particular stream where we have our independent variable where we went out to some location in our domain, and then we measured the dependent variable at those different points here. And so that's our concentration of this pollutant. The other variables that we have in this formula, C0, K, and U, are what we might call parameters. And so this model represents pollutant concentrations in a river that could be used in lots of different rivers, in small streams, in big streams. The model is valid for all those. C would always be the concentration, X would always be the distance downstream. But if I go from one river to another, the C0 value can vary, the K value can vary, the U value can vary. So those are our parameters that are that refer to a specific kind of river. Often we don't know those parameters. Okay, so this is not a super complicated model. There are much more complicated models for pollution and rivers and atmosphere and treatment processes, etc. But here we have three different parameters. Okay, and so the idea here behind this problem is that we kind of know what C0 is. Maybe I know the amount of flow in the river, and I know the amount of pollution I'm putting in, so I can figure out what this initial concentration is, and it's 100 milligrams per liter. And then the velocity of the river, that's something I can go and measure with a tool. But if you think about this decay rate, how quickly it's going away, that's not something I can necessarily know as easily. I might be able to go do a lab experiment and figure it out, but it could be different in the field. And one way that I might try to figure out what the value of K is simply to look at some data. And so that's the idea here, is that we're given this data and we're trying to figure out what the value for K is. So how would we do such a thing? Well, if you look closely at this model, one approach that we can use to do it is with regression. Okay, so we have observations and we need to find the best value of K here to fit the data to a model. And so then we can reduce, we can say like we reduce the data from having, you know, these 10 measurements down to just 2 parameters using linear regression. So I can rewrite this equation actually, or this equation rather, in a linearized form. If I take the log of both sides, then I end up with, or I'm going to take the natural log actually of C, and that's got to be equal to the natural log of C0, and then this all comes down out of the exponent. Okay, so if I take the log of this guy, it's ln c equals ln c0 minus kx over u. And so what I'm going to do here is a linear regression. So I'm going to just write linear regression up here. And this is my linearized form of the equation. And I'm going to go ahead and make it look a little bit nice to try to break this up and make it more clear. Okay, so anyway, this is a linearized form. So what happens is we have observations of C. We can take the natural log of those, and we have different points x. And if I make a plot of ln c versus x, then it should be linear. And the slope of that line, remember that y equals mx plus b is the formula for a straight line. And so here our m would represent negative k over u, and our b would represent the ln of c0. And so if we do a linear regression here on this, after I take the log of the concentrations, I should be able to fit a line to that. The slope of that line will be the natural log of c0, or it should be. It's not going to come out to be exactly this 100, I can tell you now. But and then the slope of it should be negative k over u. And so we said we already know u, so then we can figure out what k is. So we can do the linear regression of this by doing ln c, which has units of ln of milligrams per liter, if you needed that. So equals ln of c. And I can just, boom, copy that down. And so now I'm going to then make a quick plot of this. Excel has a really handy feature. You can very quickly grab the linear regression from a plot, so I'll show you how to do that. So we'll make a scatter plot here. You'll see it has two different, it's got both the C and ln c, so I'm going to delete, or click on this, delete the C values, and I'm left with the data here. I can quickly add a couple of titles. So the y-axis here is log of, or natural log of C, and the x-axis is x in meters. And we might want to make this just a little bit bigger font. All right, and let's move this guy down here a little bit. Okay, so we can do a linear regression on this now. Linear regression is just a way of fitting a line. And so add trend line. And it can actually fit different ones. And we actually didn't have to do a linear regression. We could do it with a power or an exponential regression, but it's not as useful to talk about that. So so what we want to do now is display the equation on the chart, and we're going to display the r squared on the chart. And so the equation here, let me make this font just a little bit bigger. There we go. So you can see here that the slope is negative 0.023 and the y-intercept is 4.717, and the r squared is 0.95. So the r squared is really a way of representing how well a model fits a data set. And the definition of r squared is it's the explained variability divided by the total amount of variability. And so this might tell us that 96% of the variability is explained by this model, which means that it's a pretty good model for this particular data set. Okay, and so we have our slope and y-intercept and r squared. So most people would have figured out how to do things like this in Excel before. I wanted to show you quickly a little function called LINEST that can be used to grab these values in a cell. So if I want to calculate now the value of K, I need to get these out of this cell, or out of this chart and into a cell. And so there's this function called LINEST that you can use to do that. And it is actually an array function, which means that what it does is it returns 10 different values that are related to this regression here if you do it. And so you have to select like 10 cells to get all the output from LINEST, so linear statistics. So to use it, we're going to do equals. So I'm going to grab these 10 cells. It's 2 wide by 5 tall, 2 columns, 5 rows. So we'll do LINEST, and then it asks me for the y values first. So I'm going to select the y values, and then it asks me for the x values here, which is x. Then it optionally asks me if I want to set the intercept, so you can actually have it, you can force the intercept to go through something. We didn't do that here. So we're going to want to keep it normally, so I'll make that argument true. And then it asks us if we want these additional statistics. So we can either just get the first 2 values, which are going to be the slope and the y-intercept, or we can have it return these other statistics. So since I would like to get the r squared here also, I'm going to go ahead and have it do that also. Then I'm going to close it. And so here's a kind of key trick you have to know when you're working with arrays in Excel. You hit Control, Shift, and Enter, and if you just hit Enter, it'll only do the one cell. But if you hit Control, Shift, Enter, it should do all of them. Okay, and so if you see here, this is our slope, 0.0227. We have it here exact instead of like manually copying it. This gives us a way that, if I update the numbers, I can automatically update my value for the slope and the y-intercept, and then get my value for K, which is what I'm trying to do here. So it's always nice to be able to have an automated process to do all this for us. It decreases the chances of mistakes and saves time, etc. So this is the slope, this is the y-intercept, and you can see here's our r squared here down in the 3rd row. It has some other statistics about the f statistic, and these are like the error in the estimate for the slope and the y-intercept. So there's an estimate here that we're being given. This tells us kind of how good an estimate it is, basically looking at these stats. And so there's some other statistics you can go read on those. But so the main one I need here is this is slope and this is the y-intercept. And so now I know that I can get the value of K. So I'm going to make another one up here. We'll call it model fit. And so I'm going to need a value for my model. I have C0. Why don't I just copy this? C0U, and then I need a value for K, and that's going to be in hours to the -1. And because I'm a little bit picky, I will make sure to get my -1 superscripted. And so the value of K is just going to be equal to, so we're saying that -0.0227 is equal to -K over U. So that means that K is equal to this times -U. So equals this thingy times a negative that, and 0.227 hours to the -1. Technically, when we fit this K, we were also telling it to fit C0. So even though we know C0, we really should use the C0 from the regression to get the correct model fit. So the y-intercept here is 4.72, and that represents ln of C0. So if I want to get the C0 that's actually associated with that, I need to do exp of that number, and that will give me the value. And so you can see that it's 112, and that's a little bit bigger than the 100. And so you can argue that maybe we didn't know this number that well, and that's a reason for doing that. But really you should go ahead and use the fitted value for both of them, because we fit them both here at the same time. So if we use K without changing that, we actually get a model that's a little off, and we'll look at that for a second. Okay, so quickly now what I want to do is I want to make a plot here. I'm going to copy this data from over there, here, and I'm going to change this to observations and model. And what I want to do now is, so at each of these I have an observation, and then my model is equals C0 F4 to make it stationary times EXP negative K, I'm going to hit F4 to make it stationary, divided by U to make it stationary, and then times X. And so that one I'm not making it stationary, so that when I copy, it'll copy it down. And so I'm picky here. I'm going to make it 1 decimal, and I'll hit that, and it'll copy it down. And now we can quickly pull together another graph where we compare the goodness of fit. And so here's our, let's just focus on this part of the graph now, model fit. Here's our model. And so we'll linear regression fit, or model fit maybe, we'll call it. Likewise, we should have the axis titles there. Okay, so we'll have, this will be concentration in milligrams per liter. X here is going to be in meters. And boy, this font is small. All right, one more time. There we go. And for some reason, it always makes gray font. So now we've got the data and the model. Normally when you plot, so this is important, when you make a plot of a model versus data, you want to represent the model as a smooth line, generally good practice. So I'm going to format this, and I'm going to make the marker, I'm going to have no marker, and then the line here I'm going to make a solid line, and that's for the one data series. So you can see this is the smooth fit for the model. I might want to move this up here where it's a little bit easier to see, and then maybe we want to do that. Yeah, now it's looking a little easier to see. And then, you know, for my data, I might want to play around with that. So let's change the marker options to make them slightly bigger. I like the boxes with no fill, and then with the border here around the edge of the boxes, you can change all these settings. I'll make it red, and I'm going to make the lines a little thicker. I'm going to go up to 1.5. All right, so now we can see our model, and so now we've got something that looks pretty good. Okay, so this shows how the fitting that we did matches the data pretty closely using linear regression. Let's just quickly look at what happens if I change C0 to 100. You can see that it kind of underfits everything. And so if we want to use this value of K, we really should also use that other value for C0. And so this shows you how you can fit a parameter value. The key thing here is that we needed to be able to write this equation in a linear form, and then we were able to, you know, come up with this regression from the data in Excel. You are not always going to be able to write a model in a linear form like this, and so when you can't do that, there's another approach, and I'm going to make another video where I talk about how you would use that approach for this particular data set next.